We're going to talk about log properties in this video. So there's quite a few of them, so you might want to write them down on a card or something. The first log property, and by the way, each of these log properties can be proven algebraically, but I'm not going to show you that. I just want to give you the properties. If you take the log of an argument and your base is the same as the argument, that's always going to equal 1. So the log of A, base A, would equal 1. So if you want the log of 7 and the base is 7, then that's always going to equal 1. Now on top of that, you could actually throw in, you could say that the natural log of E is 1, because remember the base for natural log is E. And you could also say that the log of 10 is 1, because the base for the common log is 10. So you could say that as well. Okay, the next property says that the log of 1, regardless of the base, is always 0. So the log of 1 base 5 is 0, and again, it doesn't matter what this base is, the log of 1 is always 0. And that's because if you take this base and raise it to the 0 power, you always get 1 regardless of what this base is. Now this property says if you take the log of a to the p and the base, the base of the log is the same as the base of this exponential expression, then the result will always be this power p. So for instance here I have log of 8 cubed base 8, and since the base of this exponential expression and the base of this log are the same, then based on the property, then this answer would be 3. Now in this example I have the common log of 10 to the 2x. Now the base of this exponential expression is 10, and remember it's assumed that the base of the common log is 10. So since those two bases are the same, the result would simply be the exponent 2x, the power 2x. And then here the base here is e, and the natural log is assumed to have a base e. So the result of this log would just be the power x plus 1. Okay, now here you have the log of a product, and it turns out that the log of a product is actually the sum of the two logs. So for example, if you had the log of x times z base 3, you could write that as the log of x base 3 plus the log of z base 3. You got to carry the same base forward. And then there's one for the log of a quotient. The log of m over n base a is the log of m base a minus the log of n base a. So if you had the log of x over y base 3, you could write that as the log of x base 3 minus the log of y base 3. Now make sure you get these properties right in your memory, because you could actually, it's just easy to think of these different ways. So make sure you memorize these two properties. Okay, now this property looks a little bit like number 3, but the difference is in number 3 these two bases were the same, but in this one the two bases are different. Okay, so in this one, when the bases are different here, you obviously can't just write that this equals the power, but what you can say is that this equals the power times the log of that base m. So for example, if I had the log of 5 cubed base 2, well, since these bases are different, 2 and 5 are different, I can't just say it equals 3, but what I can say is it equals 3 times the log of 5 base 2. Similarly here, the base 4 and the base 7 are different, but I can say that this is equal to this power 2x times the log of 7 base 4. So this property is handy in solving exponential equations. Now these two are called the one-to-one properties, and it basically just says that if the log of m is equal to the log of n, then m must equal n. Of course the bases have to be the same here. M must equal n. So this is helpful, like if you wanted to solve an equation like log of 2x plus 1 is equal to the log of 6, Both of these are base 10 logs, so you could just drop the logs and set the two arguments equal. 2x plus 1 equals 6, and then you can solve that equation. Here it just goes the other way. If two things are equal, then their logs are equal as long as you use the same base for each log. So for instance, if I have 3 to the x equal 25, then the log of 3 to the x must equal the log of 25 as long as I use the same base on both sides. Okay. And then this last one says that if you take a base a and raise it to the log of some argument base a, you just get back that argument. So for instance, if I took 9 and I raised it to the log of 5x base 9, since these two bases are the same, it'll just give me that argument, 5x. And now if I do e to the natural log of 3x, then base e, well remember the base of this natural log is understood to be e, so the two bases here are the same, so that would just give me 3x. And likewise, 10 to the common log of 8 would just be 8 because the base of the common log is 10 and this is base 10. Now, I'm just going to show you a couple of problems that allow you to solve or practice the log properties. I'm sorry, not solve, but this allows you to practice the log properties. So let's say you wanted to write the log of this expression as a combination of several logs. Well, the first thing I would do here is I would write the square root of z as z to the 1/2 power. And you'll see why in a minute. But anyway, now remember the property says that if I have the log of a quotient, you know, the log of m over the log of n, I can write that as the log of m minus the log of n. Okay, so that allows me to do that. Now here, in this log, I have a product. I have the log of m times n. So if I go to that log property that says the log of m times n is equal to the log of m plus the log of n, then I can break this log up into two logs. I'll just bring the third one down. Now in the last step, remember if you have the log of an argument to a power, you can write that as the power times the log. So the log of x squared can be written as 2 log of x. The log of y cubed can be written as the 3 times the log of y. And then the log of z to the 1/2 can be written as 1/2 times the log of z. Of course, they all have to have their bases, base 3. Okay, so that's how you take a log and write it as a combination of logs. But you can also go the other way. Let's say you have a combination of logs and you want to write it as a single log. Well, here you can take this 1/3 that's multiplied by this log and you can move it back here to an exponent. That's one of your log properties. It's just going the other direction. So I can write 1/3 times the log of x as log of x to the 1/3. And likewise, I can write 2 times the log of y as the log of y squared, and I can write 3 times log of z as the log of z cubed. Well then, notice here I have the log of m plus the log of n, and remember if you have the log of m plus the log of n, you can write that as a single log of m times n, and then I'm going to bring down the other term minus log of z cubed. Well now I can treat this as log of m minus log of n. So now I have log of m, where m is this product, minus log of n. And if you have log of m minus log of n, then that's the same as the log of m over n. So I just write it as the log of x to the 1/3 y squared over z cubed. So I can go either direction using those log properties. And again, these two problems were just a matter of writing, practicing your log properties. Okay, now sometimes we need to change the bases. So here's a change of base formula. This allows you to change the base of a log. If you have the log of, say, the arguments x and the base is a, you can pick any base you want. And you can write this as the log of the argument with the new base divided by the log of the old base with the new base. So we can use any base we choose, but it just makes sense to use base. Like for instance, log of 50 base 7, I could write that as log of 50 base 3 over log of 7 base 3. Or I could write that as log of 50 base 5 over log of 7 base 5. Or I could even write it as log of 50 base 15 over log of 7 base 50. But none of those would actually help me simplify the log because I don't have these log functions on my calculator. So what you would want to do is you could go two ways here. You could write the log of 50 base 7 as either the natural log of 50 over the natural log of 7 using the base e, or common log of 50 over the common log of 7 using base 10. Because if you did these, if you wrote it as this or wrote it as this, these keys are on your calculator, so you could just go to your calculator and punch in log of 50 divided by log of 7 and then get the answer, 2.01. And by the way, remember what you're getting. You're getting what power you would raise 7 to become 50. So if you wanted to check that, you could raise 7 to the 2.01 power, and you would see that it's going to be approximately 50. So again, if you wanted to find the log of some weird argument to some weird base, you could just convert it to either natural log or common log. So here, if I want the log of 26 base 3, then I could write that as the natural log of 26 divided by the natural log of 3, or the common log of 26 divided by the common log of 3, and you'll get the same answer no matter which one you do. And then I'm going to end on one last property here, or one last problem. Let's say that you had the log of 5 base b equal to 2.236. In other words, just say you were given this, and the log of 2 base b is 1.547. And let's say you want to find the log of 50 base b. Well, since you're given the log of 5 base b and the log of 2 base b, it seems to me like maybe you can write the log of 50 base b as some sort of combination of 2 and 5. Well, actually I can. I can write 50 as actually 5 squared times 2. So log of 50 would be the same as the log of 5 squared times 2. And then I could use my log properties to rewrite this as log of 5 squared plus the log of 2. And then I can take the log of 5 squared and write that as 2 times the log of 5. So I have 2 times the log of 5 plus the log of 2 base b. And now I know that log of 5 base b is 2.236. And I know log of 2 base b is 1.547. So if I plug those into that expression, I'll just get 2 times 2.236 plus 1.547, and that would give me 6.019 for the answer. Okay? And so again, that's just to practice with your log properties is all that's for. Now let's take a sneak peek into the next section. Suppose we needed to solve the equation 2 to the x equals 100. Well, we know 2 to the 6th power is 64, and we know that 2 to the 7th power is 128. So the answer must be between 6 and 7. But how can we get a more accurate answer? Well, we could convert this. Remember earlier we showed you how to convert this into log form? So you could write 2 to the x equal 100 as x equals the log of 100 base 2. Well, then you could actually use your change of base formula. You could write log of 100 base 2 as the common log of 100 divided by the common log of 2. And since we can do common logs on our calculator, we could calculate that on our calculator and get 6.644. And then you can check this real easy, because remember the answer should be whatever you raise 2 to get 100. And if you raise 2 to 6.644, you will get approximately 100. Okay, so this leads us into the next section where I'm going to talk about solving exponential and log equations.